In this video, we're going to talk about carboxylic acids and esters. A carboxylic acid contains the carboxyl group. Carboxyl group has a carbon double bonded to an oxygen, single bonded to another oxygen, the hydrogen on the end. This is what we would call an organic acid. I know it doesn't look like what we would typically recognize as an acid because of this OH, but because this hydrogen is easily stripped, it has the behaviors of an acid. This particular carboxylic acid is commonly known as acetic acid, which you've heard about in your first chemistry course. We have already talked about organic bases. We just didn't call them that. An alcohol is an organic base. And this right here is ethanol. So when an organic acid and an organic base react, it's the same thing as any acid and base. Water and a salt are produced. And you can see the water is produced right here. That makes H2O. Then we combine what's left of these two compounds. We have our carboxylic acid, or what's left of it. And then we have what's left of our alcohol. And this is an ester. Because this was acetic acid, anytime you make an ester using acetic acid, regardless of what the base is, the ester is commonly referred to as an acetate ester. And if you hear about acetate being in plastics and in other things, it's usually an acetate ester formed in this manner. Let's practice naming carboxylic acids first, and then we'll try esters. In this first example, you can recognize that it's a carboxylic acid because it's going to always have COOH. Remember, those O's are not bounded to each other, but they're both bonded to that carbon. If we draw this out, because there's just one extra hydrogen, I'm going to go ahead and show it. This is on a chain of one carbon, so it's methane. And to name this, we drop the E and add OIC, methanoic acid. This is commonly called formic acid. Some of these very simple carboxylic acids, we more often refer to them by their common name, and you can find this in a table in your textbook. For this class, what I want from you is if it's on that table, I'll accept either name. But otherwise, I want the IUPAC name. So my suggestion is to just learn the IUPAC naming. I'm just giving you these common names as an FYI because we talk about formic acid and we talk about acetic acid quite a bit in class. So I want you to kind of know that that's what I'm talking about here. Let's look at that acetic acid again. Again, we can see it's carboxylic acid right there. And we know that the common name is acetic acid. This has a carbon chain of 2 carbons, so it's ethane. The E is dropped, so we have ethanoic acid. And I'm sure you have never heard that term before. We've talked about acetic acid quite a bit. We've never called it ethanoic acid. But I want you to make sure that you understand the IUPAC rules. And for this, I would accept either name. I do want to talk about this, because this is how we write this formula for acetic acid when we talk about organic compounds and organic reactions. Because we want you to be able to see, oh look, that's a carboxylic acid. But in your first chemistry class, you almost certainly saw it written like this. HC2H3O2, because this is the acetate ion. And this is the hydrogen that makes it an acid. Because when it reacts with a base, it loses that hydrogen and has all that's left is this. For the compound up here, it loses that hydrogen and all that's left is that. Either way of writing that formula is correct. We just traditionally use this one when we're talking about organic chemistry and this one when we're not. Let's look at this example. So we have this carbon and then we have 4 in a row when we expand it. 1, 2, 3, 4. And then we have our carboxyl group. If we count, this is always on the first carbon. And I did not say this previously, but you don't have to tell where the carboxyl is because it has to be at the end of a chain. So by nature, we're just always going to say that the carbon within the carboxyl group is always carbon number 1. So this is a chain of 6. So it's hexane, and it just becomes hexanoic. One final one, and they get a little more complicated because you can add more functional groups and different branches, but you're still going to follow the exact same rules we've been following so far. Let's look at this condensed formula, and when we expand it, let's make it a line drawing, just so that we can practice that kind of drawing as well and recognizing it. So this first carbon, right there. We're going to add these 4 carbons, so 1, 2, 3, 4. This 5th one is this carbon, which has 2 carbons off. 1 more with a double bonded oxygen and OH. Let's count our carbons in the main chain to make sure. 1, 2, 6, 7. So 1, 2, 3, 4, 5, 6, 7. Good job. It's important that we can recognize these formulas written in any format. We can see that this is an ethane chain or an ethyl chain. There's a branch. 7 is heptane, so that becomes heptanoic. But first we have to talk about where this function or this branch is. So 2-ethyl heptanoic acid, because we still don't have to say where the carboxyl group is. So I could add more functional groups and branches, and you would just follow the same rules we've been using and change the E to OIC, then add acid. Let's look at esters. You can recognize an ester in its condensed formula because it's going to have COOC, because it's going to have the carboxyl group, but instead of the hydrogen, it's going to be bonded to another carbon. And we can expand this out. 3 carbons, and then we have our carboxyl, and then this one has 1 more carbon. When you're naming an ester, you are considering the acid portion, and remember, from this side came from the acid, and from this side came from the base, and that oxygen could technically have come from either, though we usually consider it as part of the acid. So you're considering that this acid portion is in the main chain, and this is almost like a functional group. So how many carbons is this? 1. So we say methyl to tell us the alcohol had 1 carbon. Methyl, and this is 3 carbons, so we would say propane. We drop that E and add OATE. So this is methyl propanoate. Let's look at another example. Now in this particular example, you actually don't see COOC. You have that H in there. But it's still an ester. If you were to draw it out, the H would be over here. This is still the main part, which is methyl. This is 3 carbons, which is propyl. So this is propyl. We always name the base part first, the alcohol base. Propyl methanoate. It really matters which part of the ester you name first, because you can see that these two are just almost reflections of each other. This has propyl. This was made with propanoic acid and methanol. And this one was made with methanoic acid and propanol. So the name order matters because it tells you about what they came from and which part of the chain goes where. Let's look at this one. And we will try not to get too overly complicated with esters when we expand this out. I'm going to draw it this way this time. So there's 1, 2, 3, 4. This is the carbon that's part of the carboxyl. So we have this carbon, and then we have 2 basically methyls off of it. We know that this half is considered our main chain, and this is considered our functional group. We could say dimethyl-methyl, but because it's a chain of 3, which is propyl, and it's attached in the middle, we can also say isopropyl. So isopropyl. And this chain here has 1, 2, 3, 4, 5, 6, which is hexane. So we have isopropyl hexanoate.